fly halfway around the planet. It's almost exactly halfway. Got to go a bit further out into the Pacific. And thanks, Ralf, for letting me use your computer. So I'm from the University of Sydney. I decided to take a little bit of a snapshot on the way out from seat 66K. University is this just about there. You keep flying, you get a nice view of Sydney Harbour. The university itself, some of it looks old, but it's a trick. They built it out of very poor materials, and so now it looks much older than it is. It's about 150 years old. I'll just acknowledge the people that contributed to this up front and the funding agencies. This is a photo from the mountains west of Sydney a few months ago. Now it's all on fire. I don't know if you've heard the news, but basically there's a state of emergency in New South Wales. Hundreds of homes have been lost, and it's all a bit distressing. Nevertheless, we can talk about interstellar molecules. You're aware of the diffuse interstellar band problem. There are what we presume to be molecules in the interstellar regions which we have not yet identified, and this is actually not an insignificant amount of absorption. This is a spectrum taken from the dibdata.org database, and you see this particular band here, takes the relative flux from 1 down to about 0.9, and so there's really 10% of the light missing at that wavelength due to, we presume, some sort of carbon-based molecule. I mean, whether or not it's some sort of strange PAH or cation or fullerene wrapped in an alkali atom on a fullerene, as Croto would like to tell me. We don't know yet. We've got to do experiments. A related problem is the Red Rectangle Nebula, which I know some of you know about. I think, Jan, I met you at a conference devoted to this object a couple of years ago. If we look at the red rectangle, in the visible region we see an emission spectrum, which is also due to unidentified molecules, right? And what was pointed out by Peter Saar is that on the edge, on the hard edge of these emission bands, it looks like they line up with certain diffuse interstellar bands, and so there is a tantalizing possibility that these are the same molecules and that this structure comes about through either vibrational sequence structure or the rotational structure, and in which case this would be like a band head of the rotational R branch. The red rectangle is also one of the richest sources in the sky of the aromatic infrared bands, right? So this is the red rectangle spectrum with the UIR bands. Some people like to call them AIBs. I'm not going to argue. Let's say that it looks suspiciously like aromatic material, and the exact makeup of these bands, as many of you know, is also not really well known. We can create distributions of PAHs and say that, well, they're probably large things, but definitely it looks like aromatic material. And the sort of structure that we see, at least drawn, right? Obviously, this thing has never been measured, but I guess this is what we mean by arophatic structures, right? So it's got, yes.
Well, what we called arophatic was really 3D.
Well, this is 3D.
Kind of flattish.
Well, you imagine some sort of something that is really kind of, it's got aromatic islands, it's got aliphatic bridges, it's got bits that aren't really joined on, they're just sort of stuck with van der Waals forces, it's got heteroatoms. This structure has got everything, but of course it's never been observed, but it has been published in Nature. But we take this as some sort of a proposed model for what might be sort of out there. So I'm not really into just making things up, but I do like to do experiments, and guided by, well, a couple of things, that the red rectangle has got emission features that might be related to DIBs. Given that there is a lot of aromatic material in the red rectangle, and by the way, we can also see the C2 swan bands in the red rectangle, it's clear that it's carbonaceous and probably aromatic. And so many years ago now, it's getting on, we were motivated to try to find out what sort of fluorescent molecules we could make just with benzene. So we take an aromatic precursor and create an electrical discharge with some help from our friends here at Harvard. And we set about to try to create some new molecules. We were also motivated by the observation of a laboratory band. This particular spectrum here is from Meyer's group in Basel, where I did my postdoc, but there was discovered here in Pat and Mike's group a feature in absorption from a benzene discharge which seemed to align with the strongest diffuse interstellar band there is. And so it was my motivation to see if I could recreate this band in fluorescence, and that would give me more information about the molecule, but I completely failed. I failed in that I never reproduced this band in fluorescence. But we saw a lot of things. This is Neil Riley. He was sold on to Mike, and he's continued. And this is our whole discharge source. This horrible box. Yeah, it's dangerous. And if you scan the laser-induced fluorescence of a benzene discharge, you see a lot of things. Sometimes the discharge turns off. Don't worry about that. These features, which really show what looks like well-defined rotational structure, is in fact C3. Right? You will always make C3 when you create a discharge, and C3 is a known interstellar species. But what are these things here? Well, about that time, I had a visit from an astronomer. He's also somebody who I ran a bar with in Cambridge, England, during my PhD. He's British, but he moved to Australia and he visited my lab and was absolutely horrified to find out that I used a monochromator and a photomultiplier tube to detect photons, and slapped me about the face and said, well, why don't you use a spectrograph? Why don't you take the entire emission spectrum with every laser shot? And so I went out and spent 80,000 Australian dollars on a nice spectrograph. And literally, right, the first experiment we did with this, 20 minutes later, we had acquired this spectrum here in 20 minutes. So this is just scanning the excitation wavelength with an OPO and then taking the emission spectrum at every point, and you just get this marvelous two-dimensional fluorescence map of the products of a benzene discharge. And what you can see are these lovely parabolas, these streaky things. There's a little spider down here, and most of this we can attribute to well-known species. Okay, so all of these things, these curly things, are C2 swan bands and sequences and rotational band. These are rotational band heads. All of that sort of, I don't know why the rectangles have changed size. Okay, all of this streaky stuff here are hot bands of C3. For some reason there's iodine in there. That's just because our nozzle's full of iodine at that time. Don't worry about that. But there is something, the CH down there. CH has got a nice open rotational structure with, it's like a 9-legged spider. You have PQ and R spectra going up and down. Okay, this is obviously redrawn, but if you can focus on this region here, there is a species which emits quite linearly there, and seems to, has a very rectilinear type of spectrum in 2 dimensions, which is very different to C2, and we did not know what this was. Okay, presentation has mucked itself up. This band here is 476 nanometers, and you're looking close, you can see that there is a spectrum there. Okay. We can zoom in on that now with that 2-dimensional map, and using the traditional tools of monochromators and photomultiplier tubes, we can pull out a single molecule spectrum, which looks like this. Okay, sort of plotted backwards for a spectroscopist, but maybe for astronomers it looks okay. And you see that there are a lot of features there. It's clearly not a diatomic molecule, not a triatomic molecule, it's clearly polyatomic. All that we know is that it comes from a benzene discharge and it must contain carbon and hydrogen. Okay, and there's the spectrum there to compare to this guy here. Well, what you really want to do is measure the mass. And so with mass information, then we could really start to postulate what the carrier might be. Here's Damien. He was also sold onto the Harvard lab. And Damien was my first graduate student. He now works with Christine. And he built my Rampey chamber. Okay, so maybe not everyone in here is an experimentalist, REMP stands for resonance enhanced multiphoton ionization. The exact type that I normally do is resonant 2-color 2-photon ionization. And in this experiment, we create species through some sort of discharge and expansion and take only the coldest molecules in the center of the molecular beam into another vacuum chamber, which is differentially pumped, where we interact the molecules, the neutrals, with multiple laser beams. When we create ions, they're accelerated in a time-of-flight tube, which gives us, it tells us the mass of the spectral carrier. And so, does anyone want to guess? This is the mass spectrum. Okay, discharge off, there's basically nothing there. And then there's lots of species created with the discharge. We're discharging benzene. You see there are things that are heavier than benzene. Well, do you know, Mike?
I forgot.
You forgot? This is mass 115. This species, the brightest thing in a benzene discharge in terms of fluorescence, right? After C2, C3, and CH, which are basically interstellar cockroaches, yeah, weighs 115 mass units. Okay, here's a comparison of the ionization spectrum to the laser-induced fluorescence spectrum, and it nearly all corresponds. There's obviously some feature in there that is not part of this molecular spectrum. So mass 115 corresponds to C9H7, and that can be confirmed with due duration experiments. Okay, so one can start to draw structures. You can draw indenyl radical rather, and these various phenylpropargyl radicals. And I rather was plumping for this one because C2V is my favorite point group. But it turns out, no, that's not it. The structure is the one substituted phenylpropargyl radical. So somehow, you just create a discharge of benzene, and it always likes to make this guy here. In fact, probably in fact, because this radical here is especially stable and then survives the discharge right down to where I detect further down the experiment. These are just a comparison of calculated vibrational frequencies. You see that this recipe where you basically take DFT frequencies and multiply by 0.97, this is a standard procedure to get good answers that theoreticians will shake their head at, but they know why it works. And it really matches very well with no missing frequencies, right? So there's no slop here. It's a pretty unambiguous detection. All right, so we published that in JACS. And then Neil was telling this story as part of his final PhD talk, and our colleague Leo Radem, who is a very good computational chemist, had already guessed what the structure would be because he's got such great intuition. And so Leo has actually come up with a scheme to calculate radical stabilization energies, and that's defined in terms of the heat of reaction for the hydrogen transfer between the radical and methane. Right, so what we do is we then define the methyl radical to have zero stability. That's just kind of a reference. And you find that if you react the 3-phenylpropargyl radical with methane, it's uphill by 60 kilojoules per mole. And that's already quite a lot. But the 1-phenylpropargyl radical is uphill by 100 kilojoules per mole. And so another way of saying that is that compared to methane, the CH bond at this position here is weakened by 100 kilojoules per mole. Right? And that's called the radical stabilization energy. And so what we've, I guess, learnt is something that organic chemists would have told us already, in that we tend to form things that are stable. And the motif that's appearing here is the radical stabilization energy. Unfortunately, it would have been fabulous if this was a carrier of a DIB. It misses by a little bit, but there are no prizes for missing by a little bit. So one can get a bit disappointed, but we move on. We thought it would be fun to see if we could make this species out of something that's not aromatic, and indeed it appears. And 1-phenylpropargyl radical is a generic discharge product. And I think after Neil and Damien came here to Harvard, they were just finding bands all the time of this molecule in the laser experiment here. But so we chose 1-hexine as a precursor because we figured that it could dissociate to make propargyl radicals. And we postulated that, well, propargyl radical itself is said to maybe create benzene in flames. And then maybe, you know, if you just have a lot of propargyls around, the next step, rather than haka, is just propargyls adding and adding and adding. There's a pair of elephants in the room here that, so apart from phenylpropargyl, you see a lot of stuff. It looks like noise. All of this is signal. This is just a one-dimensional laser-induced fluorescence spectrum of the products of a 1-hexine discharge. And what we see are 2 additional large peaks. Okay, so to identify those, we turn back to 2 dimensions. So this is a 2-dimensional fluorescence plot. And it looks a bit messy, I'm sorry, but what you will see is that there seem to be 2 families of species here. So if we look at the emission spectra, there is sort of a B-type spectrum, or a B1, B2, B3, and there's an A-type spectrum, A1, A2, A3. And we can pull those spectra out individually by guiding our detection, right? And so we could say this is the spectrum of species A, this is the spectrum of species B. And what delighted us was that in REMPI, so moving to the ionization experiment, on mass 65, we pull out both of them, right? And so without the fluorescence experiment, if we just did the REMPI experiment, we would have found this spectrum here. And without, well, we could have perhaps done hole burning to prove that there were 2 species there, but in this case we didn't need to. So mass 65, well, we can start guessing some more, but we know that this is not cyclopentadienyl radical because the spectrum of that guy is in the ultraviolet. This is in the middle of the visible, well, in the blue part of the visible region. But by now we've got some intuition. We know that we've already formed a phenyl-substituted propargyl radical. And so we can start to guess that, well, maybe what we've got here is a vinyl-substituted propargyl radical. And here are the experimental frequencies. There is now only one missing. For some reason we don't see nu14. But the trans 1-vinyl propargyl radical, you know, calculated using the recipe that I mentioned before, matches up very, very nicely with the observed spectrum. So, well, if one of those bands was trans vinyl propargyl, I'm going to give no prizes for people guessing that the other guy is the cis isomer. And Leo very helpfully calculated for us some energetics. I don't really know what this level of theory is, but I'm assured it's very good. So probably though, I mean this is, so 3000 wave numbers, right? It's like 0.4 eV or something like that. 0.45 eV. Probably what happens is these species are formed and then trapped over here or over here, right? As the discharge cools down in the supersonic expansion. And we see both species present. So there are 2 conformers. And just checking, right, here is the other spectrum. And the calculated, okay, cis 1-vinyl propargyl matches up really nicely with the observed spectrum. Again, nu14 is not measured. So, well, what have we learned? It seems that this radical stabilization energy is what's really guiding the formation and the survival of small to medium-sized carbon-based molecules in our experiment. These things do not carry diffuse interstellar bands. All right, and at this stage, you could start to get angry and channel this creature here, who is this is Golem, who's always lusting after the ring, right? So you can get, as a laboratory-based spectroscopist, you can be completely obsessed by the diffuse interstellar bands, and you'll turn into this guy. So it's maybe good when, you know, if people are dealing with other problems like actual interstellar molecules rather than just posited interstellar molecules. But now with an understanding of resonance stability, of the radical stabilization energy, we know that this is conferred by resonance, right? So all of those molecules that I drew, you can move the radical site around the molecule, and any organic chemist will tell you that that confers stability. So, moving back to Kwok's illustration, which could be more 3D, but maybe it would be less clear, then what we know is that if we had in this arophatic structure, right, the opportunity to break a bond, the weakest bond will not be a normal CH bond, right? It will be a bond such as this one here. And that's because in this is again just an illustration, if we break that bond, it will create two resonance stabilized radicals. A carbon-carbon bond is normally about 350 kilojoules per mole. I don't speak kilocalories at all. I can't do it. But 350 kilojoules per mole. If you have a resonance stability of about 100 kilojoules for each fragment, that will reduce it from 350 to 150, right? And so just imagining, the dimer of the phenylpropanol, then this is actually quite an unstable molecule. And so any sort of moderately sized photon could potentially break this up. And so with that idea, we thought, well, okay, let's just imagine then that if such structures exist and if they are being photoprocessed in the interstellar region, then the sorts of molecules that should be liberated first are going to be resonance stabilized radicals. So with that in mind, we set about to measure as many of these as possible in the lab and torture ourselves. And over the last couple of years, we've got more radicals than this, but all of these sorts of structures we've measured in the lab. And you know that none of them carry DIBs, otherwise you'd almost certainly know about it. But we've got up to structures as large as this pyrenyl methyl radical, and by now we're starting to exit the visible region, right off into the near IR. All right. But we've had some nice tantalizing surprises along the way, or just more torture. Here are the naphthyl-methyl radicals. They're kind of nice. You can just buy naphthalene from Aldrich and then create a discharge, and you tend to abstract some hydrogens and make these radicals. What's interesting though is you also isomerize, so you see that in the two naphthyl-methyl spectrum there is some contamination from one naphthyl-methyl and vice versa. But this contamination is from the discharge. It's not from the purity or lack thereof of the precursor molecules. These molecules also fluoresce, and this is where it gets extremely tortuous. So here is this is the observed origin band of this species here, right? Which we posit to be the sort of molecule that might be created from the breakup of large arophatic structures. We can create a reasonable simulation at a reasonable temperature of 40 Kelvin. We have used the VLT to acquire very high resolution spectra of the red rectangle a long way from the center, out to 15 arc seconds. From the spectroscopy of the red rectangle, we know that it's receding from us at 18.9 kilometers per second, and we can make the appropriate correction and apply the appropriate velocity distribution and take this 40 Kelvin simulation, and with no free parameters, just what's measured in the red rectangle, the simulation becomes this dark line here compared to what you see is the real red rectangle spectrum. And that, you would say, is a match. Except that this molecule, yeah, it fluoresces, that's great. But the fluorescence spectrum has got other bands, and they don't seem to turn up in the red rectangle, right? This is extremely annoying, because I got excited about this for like 20 minutes. This is a fluorescence spectrum. We always get much hotter molecules in the fluorescence experiment. In the REMP experiment, where we're detecting in the skimmed beam way downstream, you get a much smaller rotational profile. The temperature is more like 5 Kelvin, and you see this is it compared to the nearest diffuse interstellar band. And I guess I'll take what I can from this and say, well, at least they have similar widths. Obviously not the right species. But it does make you think, right? Yeah, we'll get angry. Some other resonance stabilized radicals were formed. We tried to make indanyl radical. right? So we take indene and we wanted to abstract one hydrogen from here, and we never saw that. But what we did see, this is meant to change, is the indanyl radical. So indene in a discharge ends up adding a hydrogen. And we measured the spectrum and we can completely identify the radical and calculate the vibrational frequencies. But the spectroscopy is not what's interesting. In fact, it's hardly interesting at all. The question is more why. And this is another moment to be upset that this is the measured diffuse interstellar band, this is the measured molecule. There's no match, we get angry. In the same discharge we see the spectrum on mass 115, that's of course phenylpropargyl radical. We also see addition of OH, which gives a hint to where our hydrogen atoms are coming from, in fact. And that's another story, but Hawaii is not the only humid place, let's say. So here's, I promised you, Ralf, to show this piece of chemistry. So this is the C9H9 surface, and if we zoom in there, right, what we find is that radical 23, it's like the Michael Jordan radical, right, is accessible from indene plus H with what is coded here as a barrierless reaction path. But I'm not sure, you can tell me, Ralf, has this been updated? Because I think I saw on your slide you'd indicated a barrier.
This was at a lower level than Alex did recently, so this was updated. So there seems to be an entrance barrier.
So there could be a barrier.
It's a very small one.
Oh well.
But there is one.
Nevertheless, so just following from what we read here, though, I thought, well, okay, if you have indene moieties then on interstellar grains, and if they have a barrierless addition of H, well then maybe they act like a sponge for free hydrogen atoms, right, in the interstellar region. And this is just another sort of zoom in of that region there. Well, so you can imagine then, okay, on our arophatic structure, if we do have indenes, then perhaps they will absorb hydrogens, and then we get a distribution of chromophores, right? And so we tried to test this by looking at some methyl indenes and so on. And, well, we start to get kind of complicated spectra. We can lose a hydrogen and we get this phenylallyl chromophore, and we measure this. We always add OH, and this is the guy that we wanted, the mass 131, which is the analog of the indanyl radical with a methyl group there. So what's of interest here is to see whether or not, tying on an aliphatic group shifts the spectrum enough to maybe create a diffuse interstellar band as an embedded chromophore in a larger organic molecule. And the answer is probably not. So we measured a bunch of these things, and we find that the distribution of peaks, this is superimposed only for fun on this region of the spectrum, right? The point was that if you have a distribution of chromophores with slightly different aliphatic connectors, it will broaden the spectrum so much that it's not consistent with the diffuse interstellar bands, right? This is a very very broad, right? Tens of angstroms broad, and there are basically no DIBs that broad. Okay. So, the upshot of this is that probably radicals, PAH type radicals, are not responsible for diffuse interstellar bands. And we can kind of rationalize that in many ways, but also it turns out that those transitions are kind of weak, right? You get a transition from the highest fully occupied orbital into the singly occupied orbital, and from the singly occupied orbital into the unoccupied orbitals, which have got comparable oscillator strengths and comparable energies, which means that then when we think about the excited states that are brought about by those transitions in terms of configuration interaction, well, they actually interfere, and the lowest energy transition ends up being very, very weak. Nevertheless, the cations may well absorb more strongly. And all of these radicals have got have got quite low ionization energies, and it could well be that they exist in the interstellar medium as cations. And so what we did is we set out to measure the spectrum of a cation in our lab in a way that's slightly different to what has been done before. And what we'll do is we'll start off with H addition to naphthalene, so we know that we can add H's to any PAH. And we know now by mucking about with deuterated water and adding water to our discharge that all of the H atoms are coming from water. Like we would take toluene D8 and discharge that and only see H addition. And that made us start to think about tunneling and all this stupid stuff. It turns out all the H is from water. And metastable argon atoms will react with water with a cross-section of 100 square angstroms to break them up and liberate hydrogen atoms. So we can, in any case, we can do this easily now. And so if we co-discharge just vapor pressure of water or heavy water with naphthalene, we will create these sort of hydronaphthyl radicals. And here is the spectrum. Okay, this is an ionization spectrum, and I'm just going to point out that we scan this laser here and fix the ionization laser. All right, this is not the first detection of this radical. Tim Zwier at Purdue had already published the spectrum. Okay. So then, what we were then able to do is create extremely cold cations right there in our chamber, right? Because if we fix our visible laser on the origin band of the radical, we're then selecting one isomer of the radical using spectroscopy. And we sit right in the middle of the band, selecting only the lowest or as low a J distribution as we can. So we have essentially 0 Kelvin vibrational temperature because we excite through the origin band. In the cations that we're going to produce, there's going to be no vibrations and only low rotations. Okay, we then fix the ionization laser at the threshold. The ionization energy for the radical is 6.57 eV, and we can walk up and down that curve, and we can sit, right there, so that it's impossible to create any vibrational excitation. And so through the spectroscopic selection here and here, what we do is we create an ensemble ready for studying of extremely cold protonated naphthalene molecules. Right? So the radical, when ionized, becomes essentially protonated naphthalene. We're lucky that the group that used to be in Orsay, Jouvet's group, he's moved to Marseille now, had already published the spectrum, a spectrum of protonated naphthalene, which we could look up, and that guided us as to where to look in the spectrum. And so by then monitoring these ions and then scanning a third laser, so this is like a triple resonance experiment, we can then deplete the ion signal by multiphoton fragmentation of the resulting cations. And so we then sit there, scan away, and we get DIBS, and these all correspond to absorptions of our, if I'm allowed to call it, I want to call it ultra-cold cations, but I think the atomic people probably have taken that word. And because we know that our spectrum is absolutely free of hot bands, we're able to assign it unambiguously. And here's a comparison of the Jouvet group, their spectrum, which is a perfectly good spectrum, but using our technique, we're really able to get much, much higher resolution. These peaks are about 2 wave numbers wide, right? And that's essentially like a 5 Kelvin rotational envelope. And I'm sure you're not interested by all of the assignments, but one can make assignments in a logical and non-ambiguous way. We actually published this just the other day, and we had some very helpful referees who asked us to look closely at this profile. And what was interesting was that when we did look at the rotational profile of this of the cation, we saw only limited amount of rotational structure. And in order to fit it, so the experimental points here in circles, right, in the rotational simulation based on ab initio data suggested there should have been a dip in the middle of the band, right? With the mixed band type guided by the ab initio transition dipole moments. In order to fit this, we had to put over the top a 1.1 wave number Lorentzian, right, which indicates a 5 picosecond lifetime. And that might be very surprising, but bear in mind that protonated benzene basically has got no vibrational structure in its spectrum. It lives for less than a single vibrational period. It distorts out of plane back onto and crosses back onto the ground state surface. So it's not ridiculous to suggest that the protonated naphthalene should undergo similar sort of dynamics. And given that the thermodynamics suggests that we need two blue photons to be absorbed, this suggests a mechanism whereby we absorb a photon from the ground to excited state, we then cross back to the ground state surface within 5 picoseconds. And of course, because this is gas phase and not solution phase, we don't come back down here. We're not going to be emitting infrared photons just at this time. We absorb another photon and then can cross back to the ground state surface and easily dissociate. Another interesting point, though, is that this gives a mechanism to cross efficiently back to the ground state surface, which I believe is required for, to efficiently emit infrared light in terms of the UIRs. And that it's often put that you need to be a very large PAH before you get those sorts of efficiencies. Well, I'm saying that at least this evidence is suggesting that protonated PAHs, at least this small one, cross very efficiently back to the ground state surface. And left alone in the interstellar medium after absorbing a photon in the visible region, this will of course fluoresce in the infrared region. Or indeed, well, we can talk about Poincaré fluorescence, Philippe, later. But it's an interesting question. Okay, so you'd think that 3 lasers is not is enough, but I then thought, oh, maybe what we can do now is to extract infrared spectra of these things. So first of all, what we did is we then went back to the radical and monitor the radical ionization signal as a function of scanning a preceding infrared pulse. So what we can do then is shelve molecules and protect them from ionization by storing them in an excited vibrational level, and this works. You're combining these 3 laser beams, 1 ultraviolet, 1 visible, and 1 infrared, into the chamber, and we can indeed extract some CH stretching bands. I don't know, Jan, you're laughing at the quality. Astronomers should be happy with this.
Experiments with 3 lasers is so cool.
Well, we're going to try 4, but and this matches up pretty well with what's already been observed. So this protonated naphthalene has been studied before in different ways, so we know where the bands should occur. But what we really want to do here is hone our experimental skills, or those of the postdoc and graduate students, so that they can really start to perform new spectra on new species. So I thought, see, with 50 slides, I thought I would well and truly go over time. I don't know, I'm probably under time, am I? And no one's going to complain. All right. So here's the idea. So we already have a pretty good depletion spectrum for the cation, where you know that we fix these 2 lasers and then deplete the cation signal by fragmentation. If you can then intervene with an infrared pulse, one could protect cations from resonant fragmentation and then reveal the infrared spectrum of the cation. And this is what I had hoped to present at this meeting, but unfortunately it hasn't worked. So as of this morning, there was still no data from Sydney, and so I'm sorry to disappoint you. We have not yet performed the 4 laser 5 photon experiment, but we'll give it a go and hope that we don't turn into 2 disfigured creatures before too long. And so thanks for listening.
Thank you very much, Tim. Questions?
I would be interested to know if you think the last experiment is actually going to work.
Well, so the problem is that I don't think there's any problem with the scheme. Okay? The problem is that these stretches, and our infrared laser doesn't stretch to any more intense bands, unfortunately. But with the energies that we have available, we're already pushing the signal-to-noise limits with this spectrum. And so I think that we've just run out of signal-to-noise with the final spectrum. About whether it should work, I say yes. So this relies on the origin band of the cation shifting by at least 2 wave numbers, essentially, or what becomes the new origin band, if you like, the sequence band for one quantum of CH stretch, yeah, in the cation should be at least a few wave numbers shifted. That's all it needs to be, and then the resonance will be shifted away from the blue laser that we use, and then the depletion should go away. And so this sort of undepletion should work. But it's a bit, I don't know, a bit extravagant, I agree. But it's fun.
I know how difficult it is.
Any other questions? If not, then let's thank Tim again. So we'll reconvene at 2 o'clock, is that right? 2 o'clock.